you have lowered the average energy of it, because it is the average energy of those states which are occupied. Empty levels don't count in the average energy calculation, right? So now overall energy has decreased. That's why there is a formation of a superconducting phase below a particular transition where this gap opens up. The concepts are similar. The same concepts are here also. That means whenever the gap opens up, it tends to overall energy is reduced. So that formation of gap is favorable. Okay. Okay. Now there is another concept which is interesting. It's called the nesting of the Fermi surface. Nesting of the Fermi surface means that there is a wave vector. If I translate the whole surface by a particular wave vector q, for example, then that part of the Fermi surface where I am translating onto another part of the Fermi surface, they are exactly identical. It just fits there. So it's like nesting this. This is analogous to here. What if you write these Brillouin zones? Okay, this is, let's say, 2 pi by a minus 2 pi by a and so on. It's called the repeated zone scheme, right? It's called the repeated zone scheme where you have first Brillouin zone between this, and second Brillouin zone is between this and this, third Brillouin zone between these two, and so on. So this is concentric. One first Brillouin zone, then second Brillouin zone, then third Brillouin zone, and so on. Okay? Now this is called the repeated. There is something called reduced zone scheme. Okay? Reduced zone scheme means what? You are trying to reduce k cannot have values greater than plus minus pi by a. So it cannot be less than that, plus minus. So you are reducing everything to the first Brillouin zone. Now how do you do that? What you do is, this is between pi by a and 2 pi by a, right? So if I take this fellow and shift it here, this one comes here. Okay, so if I translate it here, and this I translate this side, so I get this, right? Translation by 2 pi by a, right? One curve, I'm translating like this. So then you have now this part is coming here, is this part. This part is here. So in the restricted zone scheme, that is how you show the bands, right? This is the lower band, this is the upper band, and so on, and then there will be another band at the top like that, and again same thing. This will go on repeating. Okay? So you have something like this in the Fermi surface. Now, here I was talking about Brillouin zone, but you can do a similar thing in the Fermi surface. If the Fermi surface has certain topology, which has certain symmetry, then if it is symmetric to a translation through Q wave vector, that means if I translate the Fermi, a part of the Fermi surface by Q, then it goes to another part of the Fermi surface, but then it matches with that quite well, the way it does here. Okay? So that is called nesting of the Fermi surface. This is whenever there is a nesting of the Fermi surface, there is this Fell's instability or Kohn instability. Okay? Fell's instability mostly in the charge density waves, and spin density waves will be Kohn phenomenon. Okay? And both these things will give rise to either spin density wave or charge density wave. Now depending upon the Q value, this thing will occur. This is what I was talking about. That is, here what you do is that they at minus kf and plus kf, there is this gap opens up, okay, this gap opens up at kf instead of pi by a and plus pi by a, it is at kf. Okay, so pi by a, if I call it q, okay, so then it would have been q and minus q here. Here it is kf and minus kf. Okay. So this nesting is an important, nesting of the Fermi surface is an important ingredient in any such thing. So then you have this charge density wave. So let me go to the next. Okay. Here you see now, if you are dealing with a wave vector which is equal to pi by a, as I showed you, then you have a commensurate spin density wave. What does it mean? It means that the spins and the lattice periodicity is the same. Okay, and it's going from this to this. If this is the lattice periodicity, you have spin periodicity going also like that. Okay, so then it is commensurate with the underlying lattice. That is, spin density wave is commensurate with the underlying lattice. But if it is not so, that means the periodicity in the Q space, the periodicity of the spins does not match the periodicity of the lattice, underlying lattice. Then it's an incommensurate spin density wave, like shown here. Then what will happen is that there will be a spin density wave, means that the amplitude of this will fluctuate depending upon where it is, as you can see. So there is some sort of a wave. That's why it's called spin density wave, because there is a amplitude is changing as a function of Q. Okay, amplitude of these spins, spin density. Spin density means what? That is magnetic moment per unit volume, right? So volume is a very close, small volume that you choose, where you have the spins there. Okay. Yes. Okay. And your question, yesterday's question, where susceptibility can be negative if U times GEF exceeds 1. That is possible only for ferromantic instability. Once you say that it cannot be greater than 1, then that susceptibility still remains positive, because U times GEF can never be greater than 1. Okay? That is only for ferromantic thing. Once that is, spontaneous ferromantism is established only when that Stoner criterion is valid. But when that is not so, then what you expect is that the susceptibility will be there, but it is positive. It can be enhanced if this U times GEF approaches 1. It is never greater than 1. It's not greater than 1 in this particular case. Okay? So that's one. Right. Yes. Spin configuration would depend upon the Q values. We'll see that. Now you'll see it. Okay. So this part you already know, that Stoner criterion demonstrates that the electron gas is unstable against spontaneous ferromantism if this becomes large enough, and that the magnetic susceptibility can be enhanced by this factor, which is called the Stoner enhancement factor. Okay. So now if you, as I said yesterday, that what is more interesting for us is if we can get the generalized susceptibility, because the susceptibility that we are writing is at Q equal to 0. The Pauli spin susceptibility is at Q equal to 0. But for finite Q, there are many other, there's a rich physics in that for finite Q. That's what we would like to see now. But I am not going to derive the expression for susceptibility which depends on Q. Okay, it's just only heuristic arguments to show what sort of phenomena, physical phenomena will occur when Q is not equal to 0. Okay? So first thing that what we do is we write the susceptibility, which is Q's susceptibility, but in the absence of Coulomb interactions. Then it is just simply written as the Pauli spin parametric susceptibility into a factor which is dimensionless, obviously. It has to be dimensionless. So it is Q by twice Kf. You will see why this twice Kf is required later. First, let us write this susceptibility, Q dependent susceptibility, but in the absence of any Coulomb interactions. Then it is just purely the Pauli susceptibility modulated by this factor, which is a function of Q by twice Kr. Now, in presence of the Coulomb interactions, in presence of Coulomb interactions, this gets modified the same way as the Pauli susceptibility gets. So now this is nothing but this one here, and this gets modified by this factor here, which is this Q dependent factor. Now if you see that the Pauli susceptibility, that is this chi p, is nothing but mu beta square into GEF, right? So if you divide by mu beta square here, then this part, this mu beta square into GEF is nothing but chi p. Chi p into this is this chi q naught. Okay, and alpha is now u by mu beta square. This part is clear. So what it tells you is that you have a similar structure for the Q dependent susceptibility, okay, as you had for the Pauli parametric thing at Q equal to 0. Okay. Only thing is that this term gets modified. That means now this parameterization, this parameter is taking now the earlier was is u times g EF. Instead of that, now we have alpha. Only this modification occurs, otherwise alpha contains the same information. It also behaves. Now this factor is also again an enhancement factor for the Q dependent susceptibility. When the interactions are now present, because of these interactions you get this Stoner enhancement like factor in this. Okay, now if it so happens that chi q0 has a peak at some finite value of q, if that happens, then what will happen is that then in this q, this alpha times chi q0 can approach 1. Okay, if the amplitude of that, if chi q, if this has a maximum at some maximum value at some value of q, finite value of q, then at that q value this can approach 1. Okay, in which case this will be enhanced. Okay, so what can happen is that if now as a function of q I have this thing going through a peak like that, some peak, the crests and troughs type of thing, then the magnetization will also spontaneously go through that same modulation as a function of q. If I plot magnetization as a function of q, it will go through all this because of this factor in the denominator where chi q, whenever it goes through a maximum, then it comes closer to that, this gets enhanced. So magnetization gets enhanced. When it is not so close to the peak, it's slightly away from the peak where it goes to a minimum, then there will be a corresponding increase in the susceptibility. Right? Okay. So it tells that now, Okay, now these interactions are now parameterized by this alpha, where this chi and q, if it diverges at some value of q, then q is diamagnetic susceptibility. Okay, that's what we'll see. Okay, now this vector potential, we make a choice like we did last time, but now a different, slightly different choice than I had shown you earlier. So we make this choice Ax equal to 0, Az equal to 0, Ay equal to Hx. Then the Hamiltonian can be written in this form. So this is just algebraic steps. Okay, so you can write the Schrodinger equation now this way. Now, in this particular case, now we assume that it has a solution which is this type of solution. That means in the direction y and z, it behaves like a plane wave. Okay, it's a plane wave in the directions k, y and kz. But when it comes to x, we have some wave function which depends on x. Okay, so now this we try to use as a solution there and evaluate the different differentials. So finally what you get is this. This is the Schrodinger equation. Now you see that there is this term h cross square kz square by 2m. Okay, and these xy components are coming here. Okay, field is applied along z direction, remember that, because that's why we had made a choice the way we made. So there is this thing, this part which we write now as ky, we write it like this, and omega, which is Eh by mc, is, what is this omega? Omega is the cyclotron frequency. Cyclotron frequency, which is twice the Larmor frequency. Okay, which is twice the Larmor frequency. Okay, so we can express it in this form. So now you can see yourself, it has the form of a harmonic oscillator, right? Which is centered at x naught, right? As you can see, this term, you recognize this term? This term is nothing but the restoring potential. That is the potential of m omega square x square is the harmonic oscillator potential. Okay. So this is now the harmonic oscillator which is centered at x naught. So finally, you can write it in this form, where this E perpendicular is actually E minus this h cross square k square by 2m. I'll show you in the next. Which is this. Now what is this actually? This means E perpendicular is the energy of motion in the xy plane. It's a two-dimensional plane. There, whatever this motion is there, it is the energy associated with that motion in the xy plane, which is perpendicular to the direction of the magnetic field, which was along z axis. Okay, so you have z. There is happening, something is happening in the z direction, but the main action is occurring in the xy plane. So now you say that since it has this oscillator form, okay, so its energies, the eigenfunctions would be Hermite polynomials, and the energies are discrete, as you can see, the n of h cross omega. And so you can write it in this form and substitute for this in terms of Bohm-Magneton. Okay, so you will get this now. The energy is E perpendicular. As I said, you remember that this is the energy of the motion in the plane perpendicular to the direction of the field. That's a very important thing. I'll come to that later on. Where this n can have values, integer values, 0, 1 to 3. Now, this I will come to later also, but let me just spend a few minutes to explain this, okay, what it is basically. Okay. What has happened? Earlier, when there was no magnetic field, you had not applied any magnetic field, you had a free electron gas. Okay. Now, what is the topology of the Fermi surface for a free electron gas? It is spherical. Right? It's a sphere in what space? K space, obviously. And it has a radius which is equal to Kf, Fermi wave vector. Okay? That is what was happening in zero field. Once you applied the field, now what has happened to that Fermi surface? You can see now. What has happened is that it has, this spherical Fermi surface has broken up into concentric cylinders, right? As you can see, they are concentric cylinders. Overall convolution is still sphere, but these concentric cylinders represent what? They represent the levels. And these, in this plane that you have, this plane is this here. That plane, it behaves like a, so there are discrete levels. So that discreteness is coming from the harmonic oscillator, which is here, shown here. If I plot Px, okay, and so you get these discrete levels along this, which is, here it is Ef, and this is the energy. Okay, so these are distributed like this, in this plane, which is your xy plane. Okay, this is Px, Px, and Py. This is this plane, which is this. Okay, because it is behaving like a harmonic oscillator in 2 dimensions, which is in the xy plane. Okay. In the z direction, it is behaving like the usual normal thing where the density of states go as root E, right? And the free electron. Now this part I will go through. Now what has happened is that in the absence of the magnetic field, this was spherical Fermi surface, and you had all states. Gives us this one, because I'm sorry, just 1 minute. No, I made a mistake. No, yeah, this term. This term I am going to show that becomes important at low temperatures and high magnetic fields. Okay, so I am just taking only these two in that integral. Okay, we will return to this later. So this part you can keep in mind. We will do it later. So I am taking only these two terms, which were the first two terms. The third term I didn't bother. So now this, as you can see, this when it is 1 by L, and L goes from minus infinity to plus infinity, this does not contribute at all. This summation over L will go to 0. And so you are left with only this term, summation, which gives you this value because of this. You remember what is this? This must be familiar to you. Not Fourier. The Riemann zeta function. The Riemann zeta function. You can check that. Okay. Okay. So finally, the Gibbs free energy, we get it in this form. These two terms were there. So we assume that EF is very large compared to mu beta H, which is always true. Okay, because as I said, these energies are of the order of electron volts, and these are of the order of milli electron volts. So this condition is always satisfied. Then we can just make use of this result, because this is now the derivative of, this is nothing but Fe. Okay? So you have dFe by dE to dE, this integral minus infinity plus infinity would give us this. Okay? Now Fe at E infinity is equal to, Fe is a Fermi-Dirac distribution at an energy which is equal to infinity would be 0, obviously. So that is 0, and this will be 1, minus infinity is 1. So that's why this value would be minus 1. So you substitute that in, so finally you get this sort of a expression. You substitute for k, that those are those factors and so on. So you have terms which are independent of h, and there is the h dependent term which goes as h square. So finally you get this susceptibility as m by h, which is nothing but 1 by h minus 1 by h dg by dh at constant temperature. That is the isothermal susceptibility. It gives you this form, which is nothing but this one. If you now look at this form, this you can write it in terms of, our density of states. Instead of writing it in terms of EF, you can write the density of states. That relation, let me just put it for you. Actually, G this is the relation from free electron theory. Okay? So if you substitute that here, you will get your usual thing. This will be just simply minus 1/3 of the Pauli susceptibility, which was nothing but mu beta square into GE. Right? So, Landau diamagnetic susceptibility is roughly 1/3 of the Pauli spin susceptibility. There, of course, a minus sign because it's diamagnetic, whereas Pauli you have positive sign. Now, one more thing which is important here is that this is true for when we treat them as free electrons. But in a given solid, even in a metal, all the electrons are not free. Okay? So, which are the free electrons in a metal? Which electrons are free? Which electrons are free in a given metal, any metal? They are not completely free that they fall off. They are not free, that free. Right? Electrons at the Fermi surface are free. Yes, that is true. Those are in the electrons in the conduction band are free. Okay? But then all the electrons are not free. In terms of the energy, if I was to say, how do I put it in terms of energy? When I say free electrons, what do I mean? Because the electrons experience a periodic potential in a lattice. So then what? When can I say that the electrons are free? That's one way of saying, but in terms of this energy levels, I mean this, I have the periodic potential, right? Electrons will see this potential only when the energy of the electrons is, yes, less than the height of these potential barriers, right? So those electrons will be so. Here. Now, if you look at these concentric cylinders, with increasing field, what is happening is that the radius of these things are increasing. So, if the Fermi cylinder, if I take the Fermi level, which is the Fermi surface, if I consider it to be one of the cylinders, okay, then these Landau levels, which were earlier inside that, they tend to move out, go through the Fermi surface. As they move through the Fermi surface, the electrons which were there already in the Landau level, they are emptied. They are emptying into getting the energy into the KZ. That means, the energy now is in the Z direction. Extra energy that is there goes in the, so that the total energy is conserved. So every time you are increasing the field, these cylinders are moving like that. They are swelling. Okay? And every time a Landau level passes through the Fermi level, then there is a certain peak. And wherever it is midway between the two, then there it goes to a minimum. And this oscillation continues. You understand? So this is the pictorial thing. Now, interesting aspect of this was there for a long time now, but if you remember, there is something called quantum Hall effect. Okay? This quantum Hall effect was observed in a two-dimensional electron gas, which was by case of semiconductors, we are using L gas. Okay? So there you are using it's like a field effect transistor where you have a source and a drain and a gate. And the gate, it behaves like a two-dimensional electron gas. So it mimics exactly the Landau level. And whenever you have these Landau levels, you have a change in the resistivity or Hall resistivity. You understand? So that then this became quite interesting. Now I'll just show you the last picture and be done. This I told you. This was the result which was observed by these guys. D-Hess-Van curves for top one is for zinc. This is for zinc and this is for gallium. At two different temperatures. It's 2.46 Kelvin. Here it's only convolution that is given. That means it will have oscillations like this. Okay? And at higher temperature, now you look at the oscillation amplitude decreasing. Okay? And it will pick up on this side again, like this. Like, you have these beats. Beat amplitude, somewhere it will have constructive whatever interference. There the amplitude is more. And then it compute that amplitude collapses and again it picks up and so on. You have something like that. This was the